In the quantum world, observation changes reality. Not metaphorically, not in some vague philosophical sense. Literally and measurably. Before you look at an electron, it doesn't have a definite position. It exists as a spread-out wave of probability, multiple possible locations at once. The act of observing it forces it to choose a location, to commit, to become definite. The universe is fundamentally different after observation than it was before. But here's what almost everyone gets wrong. It's not consciousness that matters. It's not your mind reaching out and magically affecting matter with the power of your thoughts. The real story is stranger, more subtle, and more profound than that. The double-slit experiment is the clearest demonstration of observation changing reality, and it's been performed thousands of times with the same bizarre results. Fire electrons one at a time through two slits. Just shoot them, one by one, toward a screen with two narrow openings. What happens? They create an interference pattern on the detection screen behind the slits. Alternating bands of high and low probability. Light and dark stripes, just like waves interfering. Water waves passing through two openings create the same pattern. Light waves do too. But here's what's bizarre. Each electron goes through as a single particle. You detect individual impacts on the screen. Click, 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 one at a time. But the pattern that builds up over many electrons, over hundreds or thousands of individual detections, shows wave interference. The electron must have somehow gone through both slits simultaneously, interfered with itself, and then appeared at one specific location on the screen. That's the only way to get an interference pattern. Both paths must be taken. Both possibilities must interfere. But each electron is detected as a single particle. One impact, one location. So each individual electron somehow goes through both slits, creates interference with itself, and then manifests as a particle at one location. That's already strange enough. But here's where it gets truly incomprehensible. If you set up detectors at the slits to see which slit each electron actually goes through, the interference pattern disappears. Completely. Simply by observing which slit the electron passes through, you change the outcome. The electron stops behaving like a wave and starts behaving like a particle. With observation, particle behavior. No interference. Just two bright bands on the screen corresponding to the two slits. Without observation, wave behavior. Interference pattern. Multiple bands. The electron knows whether you're watching, and it behaves differently accordingly. Except, it doesn't know anything. There's no consciousness involved. No spooky awareness. No electron thinking about whether someone is looking at it. What's happening is far more interesting than that. The popular interpretation, the one you see in documentaries and pop science books, is that consciousness causes wave function collapse. Your mind reaching out and affecting physical reality through observation. This has spawned endless mystical speculation. The power of consciousness. Quantum healing. Manifestation. The secret. Mountains and mountains of pseudoscience built on a misunderstanding. But that's not what's happening. The quantum mechanical use of the word observation doesn't mean a conscious being looking at something. It means any interaction that entangles the quantum system with a macroscopic measuring device. Any interaction that irreversibly records information in the environment. When you place a detector at the slit, it interacts with the electron. Physically interacts. Photons bounce off the electron to register its position. Atoms in the detector get ionized. Electrons cascade through the detector's circuits, creating electromagnetic pulses that propagate outward. The electron becomes entangled with all these other particles. Correlated with them, information about which slit it went through gets encoded in countless particles in the environment. This is measurement. This is what collapses the wave function, or more accurately, what entangles the quantum system with the classical measuring apparatus in a way that destroys quantum coherence. You don't need consciousness. You don't need a human observer looking at a readout. You just need interaction, physical interaction that records information. The electron observes itself through its interaction with the detector. It creates a record in the physical world, a record that can't be erased without tremendous effort, if at all. A rock could be an observer in this sense. A detector with no one looking at it is an observer. Even air molecules interacting with a quantum system count as observation if the interaction is strong enough and irreversible enough. Before observation, the electron isn't in some mysterious superposition of actually being in both places at once. That's a common misunderstanding. The quantum state is a superposition, yes. A mathematical combination of went through left slit and went through right slit. But this isn't the electron being in two places. It's the universe not yet having committed to which history is real. which path actually happened. Think of it as potentiality, not actuality. The electron has the potential to have gone through either slit. Those potentials can interfere with each other mathematically, creating the interference pattern. Observation doesn't reveal which potential was really true all along. It makes one of them actually true. It retrospectively creates a definite history. When the detector interacts with the electron, the detector also enters a superposition. Detected electron at left slit plus detected electron at right slit. Then the detector's circuits enter superposition. Then the electromagnetic signals propagating from the detector enter superposition. Then the air molecules that those signals disturb enter superposition. Within nanoseconds or less, billions upon billions of particles are entangled with the information about which slit the electron passed through. This is decoherence. The quantum superposition spreads into the environment so rapidly and irreversibly that it becomes impossible to see interference effects. The system has effectively chosen one outcome, not because consciousness observed it, but because the information leaked into the environment in an irretrievable way. The boundary between quantum and classical isn't about size or complexity. It's about isolation. Tiny systems that don't interact with their environment can maintain superposition for long periods. Atoms in ultra-high vacuum at near absolute zero can stay in superposition for seconds, even minutes. Large systems inevitably interact with countless particles around them. They decohere almost instantly into definite states. A dust particle in ordinary air decoheres in femtoseconds because it's bombarded by trillions of air molecules. Here's where it gets mind-bending, where the strangeness goes to another level entirely. John Wheeler proposed the delayed choice experiment. The idea is this: decide whether to measure which slit the electron went through after it's already passed through the slits, but before it hits the detection screen. If you insert the which path detector at the last moment, after the electron has already gone through, you get particle behavior. No interference. If you don't insert it, you get interference. Your choice now, in the present, affects what the electron did in the past, whether it went through one slit or both. This seems impossible, but it's been performed in laboratories many times with unambiguous results. In 2007, physicists did this with photons, where the choice of whether to measure which path was made after the photons had already traveled most of the distance. The results were clear. Your present choice determines the photon's past behavior. In 2015, Australian physicists did a version using helium atoms. They could choose to measure which path the atom took after it had already completed its journey through the apparatus. The choice affected whether the atom showed wave or particle behavior for a path it had already traveled. Past tense, already happened. Even more dramatic, cosmic-scale delayed choice experiments using light from distant quasars. The photon begins its journey billions of years ago. It encounters a massive galaxy that can bend its path. Does it go around the galaxy on one side or the other, or both sides simultaneously, interfering with itself? The choice of whether to measure which path is made now, on Earth, billions of years after the photon passed the galaxy. And that choice, made now, determines the photon's path billions of years ago. But this isn't time travel. It's not retrocausality in the usual sense. It's something stranger. The electron or photon never had a definite past until measurement forced the universe to commit to one. Before measurement, there's no fact of the matter about which slit it went through. The past is as undetermined as the future in quantum mechanics. Observation doesn't reveal the past. It creates it, selecting one history from the superposition of potential histories. And this bothers me. It should bother you too, because it violates our intuition about how time works, about how reality is structured. Schrödinger's famous thought experiment was meant to show the absurdity of quantum mechanics, but it actually reveals something profound about what observation means. Put a cat in a box with a quantum device that has a 50% chance of releasing poison, a radioactive atom connected to a vial of poison gas. Before you open the box, quantum mechanics says the system is in superposition. Dead cat plus a live cat. The popular interpretation is that the cat is somehow both alive and dead until you look, existing in both states simultaneously. But that's not quite right. That's not what the mathematics actually says. The cat is entangled with the quantum device. If the device decayed and released the poison, the cat died. If the device didn't decay, the cat lives. But those two possibilities are in superposition. The universe hasn't committed to which happened. From outside the box, you can mathematically describe the system as superposed. But from inside the box, the cat observed the quantum device through direct physical interaction. The cat's fate decohered essentially instantly. Because cats are macroscopic objects made of trillions of atoms, interacting with billions upon billions of air molecules every microsecond, the cat is definitely alive or definitely dead. You just don't know which yet. Your ignorance is not the same as quantum superposition. Opening the box doesn't collapse the wave function. It entangles you with the system. Before opening, from the perspective of someone with complete quantum information, you're in a superposition of seeing dead cat plus seeing a live cat. After opening, the superposition has spread to include your brain, your memories, the photons bouncing off the cat and into your eyes, the neural signals in your visual cortex, your entire future light cone. From a God's eye view outside the universe, if such a thing were possible, the superposition persists forever. There's a branch of reality where you saw a dead cat, and a branch where you saw an alive cat. This is the many worlds interpretation. Observation doesn't collapse possibilities. It splits you into multiple copies, each experiencing one outcome, with no way to communicate between branches. Alternatively, decoherence theory says the cat decohered into a definite state long before you opened the box. But the branches are still there, just too entangled with the environment to ever show interference. Either way, it's not your consciousness that matters. It's the irreversible flow of quantum information into the environment. Observation doesn't just collapse superpositions. It can freeze quantum evolution entirely. The quantum Zeno effect. If you observe a quantum system continuously, frequently enough, it never changes state. Imagine a radioactive atom that would normally decay with some probability per second. In quantum mechanics, the undecayed state gradually transforms into the decayed state. The wave function smoothly transitions from definitely not decayed toward a superposition with increasing amplitude for decayed. But if you measure whether it's decayed every microsecond, each measurement resets the evolution, projects the system back into the undecayed state. The quantum system never has time to evolve into the decayed state before the next measurement freezes it again. Watched continuously, the atom never decays. Observation prevents change. This has been demonstrated in laboratories with trapped ions and other quantum systems. Continuous measurement can freeze a quantum system in place, preventing it from evolving to other states. It's as if the act of watching pins the system in place, prevents it from exploring other quantum possibilities. The universe only changes when you're not looking. Close, continuous observation prevents quantum evolution. This isn't philosophy or interpretation. It's measured, repeatable physics with practical applications. In quantum computing, you want to prevent qubits from decohering. The quantum Zeno effect can help protect quantum information by carefully designed measurements. In precision measurement, you want to suppress unwanted quantum transitions. The Zeno effect can freeze atoms in desired states. The flip side is the quantum anti-Zeno effect. Carefully timed measurements can actually speed up quantum transitions in some systems. Observation becomes a tool for controlling quantum evolution, not just passively recording it. So what is observation really doing? It's not revealing a pre-existing reality. It's not being influenced by consciousness. What then? Observation is fundamentally about information flow and entanglement. When a quantum system becomes correlated with the environment in an irreversible way, when information about its state spreads beyond any possibility of retrieval and reversal, when quantum coherence is destroyed by entanglement with countless environmental degrees of freedom, that's when we say it's been observed. The wave function is really a description of our information about a system. Or more deeply, it's the information encoded in correlations between parts of the universe. Before measurement, we have limited information. The system could be in multiple states. The wave function encodes all the possibilities and their relative probabilities and quantum phases. Measurement increases our information. But quantum mechanics is strange because gaining information about one property like position necessarily destroys information about complementary properties like momentum. You can't simultaneously know both to arbitrary precision. The Heisenberg uncertainty principle isn't about measurement clumsily disturbing the system like a clumsy observer, bumping into things. It's about the fundamental incompatibility of certain types of information. Position information and momentum information can't both exist with arbitrary precision simultaneously. Observation isn't neutral. It changes what can be known, what is defined, what is real. The universe, at its deepest level, seems to be made of information and relationships, not stuff. Quantum states are information states. Particles are stable patterns of information in quantum fields. Some physicists think spacetime itself might emerge from entanglement patterns. From correlations of quantum information across space, Observation matters, because information matters. When information leaks irreversibly into the environment through decoherence, when quantum correlations spread beyond the system into the surroundings, definiteness emerges. Reality crystallizes out of quantum potentiality through the irreversible flow of information into the environment. John Wheeler, one of the great physicists of the 20th century, called it from bit. Physical reality emerges from information. Every every particle, every field, every space-time event derives its existence from answers to yes or no questions. From bits of information established through observation and measurement, observation changes reality. Not because minds have magic powers over matter, not because consciousness is special in some mystical sense, but because interaction creates entanglement. Entanglement spreads information, and information flow forces the universe to commit to definite outcomes from quantum possibility. Before observation, quantum systems don't have definite properties. They exist in superpositions, clouds of potential, probability waves spanning multiple possibilities. Observation doesn't reveal which potential was really true all along. It makes one of them true, creating a definite past and present where only fuzzy possibilities existed before. This is verified by countless experiments over decades. The double-slit experiment shows observation destroying interference. Delayed choice experiments show present measurements affecting past states. Quantum eraser experiments show that erasing which path information restores interference even after it seemed to be destroyed. The quantum Zeno effect shows continuous observation freezing change. All of these experiments point to the same reality. The act of observation, of irreversibly recording information in the environment, fundamentally changes what exists. You can't be a passive observer of the quantum world. There's no view from nowhere. No objective stance outside the universe watching it unfold without participating. You're always a participant. Every measurement you make entangles you with the system, makes you part of the quantum story, forces the universe to commit to one history out of many possible histories. Your observations don't just record reality. They participate in creating it, one collapsed wave function at a time, one decoherence event at a time, one irreversible information transfer at a time. The universe at its foundation is not made of stuff, but of possibilities, woven together by quantum correlations. Observation is the process by which some possibilities become actual, and others fade into the roads not taken. The histories that might have been but never quite solidified into reality. Reality itself is participatory, constructed through the vast web of observations and interactions, measurements and decoherences, information flows and entanglements that define what has definitely happened versus what remains in quantum limbo. We don't just observe the universe. Through our measurements, through our interactions, through the inevitable entanglement of our measuring devices with quantum systems, we help determine which universe we inhabit. We help write the history that becomes real, one observation at a time. This is what Richard Feynman understood deeply. That quantum mechanics isn't just strange mathematics. It's telling us something profound about the nature of reality itself. That observation and measurement aren't passive activities. They're participatory. They're creative in a very real sense. The quantum world is watching us watch it. And in that mutual observation, through that web of interactions and entanglements, reality emerges.